And now we have started the recording. Now we are ready to talk about your questions. So first of all, let's start with the question of Elvira. Am I right? It was you, yes, who had the
Yes.
question about the task with computing of partial derivatives of this function. So let's talk a little about this task. We want to compute partial derivative at the point 0, 0. So what can you say about it? What's the problem? So let's try to do it. Let's solve it. First, as I mentioned, as I understand, you want to do the following thing. Let's compute this function's derivative. Yes, something like this one. We need to compute partial derivative. So we take this function. So we take it over x. So for example, and what do we get? We can get 3x squared, and here we need to write something like this inconvenient thing.
I'm sorry, are you transmitting your screen somewhere? I don't see.
Oh, of course, I forgot to start the screen sharing. Yes, sorry. I started the recording, but I forgot to start the translation of screen. Sorry. So, okay. We have this function. We want to compute this derivative. Am I right? I think I'm right.
Well, yeah.
So what do we have? What do we have now? And you want to say that now we can get something like this as the result, and we can compute it at the point of 0, 0, yes? Because like we have 0 and we have 1 over 0, so it's madness, it's terrible, so it's forbidden. It's uncalculatable. Am I right?
Well, but the way how I was solving it, like you start to pretend that x is a constant, right? So you
Over x, so with partial derivative is over x, so maybe y is
well, or over y, yes. So that's how I did it, and then I thought that we need just to put. Wait, I need some time because I have it written in another form.
It was just a suggestion, maybe. I just expected a problem if you write it in this form, like y is some constant, so we just write it.
For example, you can remove 3 there, right?
Yes, of course, but
3 multiplied by.
yes, of course, but that's not a problem. I want to understand what's your problem. So I expected that you had problem during submitting while using 0 and 0 for x and y here, and like you can get something 0 1 like 1 over 0 in this term, because you know that this term can be written like in this form. So number over 0, that's a problem, blah blah blah, everything is bad.
Yeah, that's my problem. That it's 0 over 0, and then when I tried to put there just the answer 0, 0, it didn't work.
Yes, because the answer is not 0. So, like, okay, we have a definition of formal definition of partial derivative. What is it? We know that partial derivative of x of like x0, y0 at the point of we know that the definition of partial derivative can be rewritten in the following form, like f(x minus x0), or like x y0 minus f(x0 y0) over x minus x0, while x approaches x0. Like, that's a formal definition of partial derivative. Using this partial definition, just this definition for point like 0, 0, for 0, 0, and for our function, we can get the following thing. Like, we need to use 0 as for y, and we need and 0 for x 0. So we can get this formally. We get the following limit formally, just using the definition, of partial derivative at the point of 0, 0. And you can see that this limit exists because you can see like it's 0, I don't need you, I don't need you, I don't need you, and this thing is x, so limit equals 1.
Okay, I see now.
So sometimes you can face some difficulties computing partial derivatives because you have some specifics, some specific of partial derivatives, especially in some extremely problematic points like 0, 0 for such functions. So that's why we can say that we have a partial derivative that equals 1. And if you, as you can imagine, the same story with y, with partial derivative over y.
Yeah, okay.
Good. Any questions? Any more questions? Maybe you want to discuss some things from SGA tasks. Like maybe you want to discuss something. I can imagine what do you want to discuss. So
Just managed in your lab, that's why maybe some useful tips from this derivatives for multivariate function, because unfortunately I haven't studied yet because of workload.
I understand you very good because I have a work. I'm a kinda overloaded guy too. So, but maybe any other questions? Any other students have any other questions? Maybe.
I can propose another one. In the lectures, the explanation how to calculate the tangent plane, well, maybe it's not tangent plane. Can you go a little bit more up, please? So, now more down.
Sorry?
Now can you go slightly more down? Yes, because I'm looking at your screen.
Partial derivatives.
So probably, can you show us one example how to calculate tangent plane? Because in the lecture, the guy used an example that, in my opinion, was not very useful. Because he used something like square root of xy. Oh no. So from his example, I didn't understand how did he do that.
Okay. Formula. To be honest, we have a specific formula just to we can use just to compute the tangent plane. Motivation. Sorry, it's better. Maybe I need this video. To be honest, I don't remember the formula. I remember that it consists of some partial derivatives, but I don't remember the full formula. 1 second, please. Yes, as I see, the only thing we need is just what but quality. Oh, you lie. I don't believe you. No. I need full HD. Like here you can see the formula for tangent plane. Like you have some specific point AB, FAB, and you just compute the partial derivatives for your function f, and you can just, I don't know, like you can say that we can take some randomly written formula, like for example this one, at the point of and we need, imagine the following: we want to compute compute the tangent plane for this function, for example, at the point of, I don't know, 1 p over 2, like an e. Like I want to build a plot here. So what can I say? Z is a function of x and y, and I can easily compute the partial derivative at the point of e over 2. It's easy. We can say that it's still exponent at the sine y in this point, like, and we know what it equals e. So I think it's easy to see. The same thing can be repeated with function over y, and we'll get cosine y, and it's easy to see that we will get something like 0. Yes, and the only thing we need is to use the formula of tangent plane, like this one. X minus x0 plus 0.5. Sorry, I need a lot of time to type it. As you can see, it's a long formula expression. But at least as you can see, it's at least it's a kind of aesthetic, because my own when I write my handwritten notes are really terrible. It's really good that you don't see. Okay, so that's how we can that's a formula that defines the equation of tangent plane, and now we can just use values in this task, and we can get the formula of tangent plane, for example, for this randomly taken function. We can plot it on GeoGebra. As you can imagine, I like using GeoGebra, so it's a really useful thing. And what will we get? This thing is e, this thing is 1, this thing is 0, so I don't need you, go away. And here we have e, so we'll get this, formally we'll give this equation of tangent plane plus z plus z minus 2e. Like, for example, this one expression. Let's check it if it works. Maybe I'm incorrect. Saying y, like it's such a beautiful thing. It's such a beautiful thing. You can see, and we can now build a formula like x ex plus z minus 2e equals to 0. And now I need a point like 1 over 2 e. And what did I get? Oh no, I got something strange. Maybe I miscalculated something, because it looks more like orthogonal plane instead of tangent plane. Am I right? Am I right in my computations? Cosine am I right? Sorry, 1 second. I think I hope it was written correctly. Minus, of course, because minus. Yes. Sorry, I lost. As usual, I lost one more important symbol. So that's why the proper formula will be the following one. So. And now we need to change a little the equation of my, and you'll get something much more natural. As you can see, with really with tangent, with plane is tangent for my function at this point. Of course, it crosses the curve in plenty of points, but that's not a problem. That's just a pity part of our life. But that's still a tangent plane. Okay?
Well, yeah, now actually much better.
So just if we have Plane formula. I will name it old plane. That's the only thing you need to know if you want to build a tangent plane for some simple formula without any tricks with derivatives and partial derivatives and something like that. So I hope now it's easy. Maybe something else. Maybe you want to discuss something else from the previous weeks. Maybe you want to discuss any interesting. Maybe you have some simple questions. Maybe you have questions about partial quizzes. So I'm ready to help you. I'm ready to answer your questions. Okay. It looks like you have none. You have no questions. So what can I suggest what can I suggest to you? We can, for example, solve some tasks about, I don't know, partial derivatives. Maybe we can solve some tasks about dedicated to the material over the first 4 weeks. We can start discussing of integrals. We can just see the difference. We can face difference between definite and indefinite integrals. What's the logic of these two structures with close to same names? Maybe we can. Maybe you have any suggestions what to do. We can compute some approximations, for example, at the point. We can compute some. We can solve some tasks from practice quizzes if you have troubles with them. So I'm ready to your ideas. I'm ready to your suggestions.
Well, I will be fine by just solving the tasks from practice quizzes. I don't know if anyone can propose something else.
Yeah, sounds nice because I thought that integrals is a little bit early because a lot of us haven't started the course week because of labs and so.
The idea was just to prepare your mind, to integrals, not to discuss some complicated things, just to show you what are we talking about. Maybe sometimes it's better to start such talks in kinda real discussion instead of watching videos. Maybe I can.
Let the integrals be when the integrals begin. Next week, I suppose.
Okay. That's just my idea is just to suggest. So okay, we can open the tasks from practice quizzes and we can discuss them. Usually students have plenty of questions about external task. So I don't know. Maybe have you seen the external task? And if you have seen it, so maybe you have any questions. It was nice. Yes, it was really good question. Really, one of my favorite tasks from calculus course. Maybe.
Am I right that it's about value theorem and in terms of proof? Yeah.
In terms
or sign of derivative.
I don't use
Like
value
for
theorem.
left neighborhood. Because they used for left neighborhood and right neighborhood, and then by the definition of the extremum itself, like sufficient and necessary conditions.
Yes, I can say that the topic of this task is dedicated to discussing of necessary and sufficient conditions. So because as you can see, the question is, do we need the change of sign event? Define the neighborhood. Yes, something like this, for example. We still have new students. Okay, we can talk about tasks from this quiz. So maybe we can discuss it. So if you're interested in it, we can discuss it. So, like for example, let's start with, first practice quiz. Yeah, Yes. So what do we need to? What do we want to say? For example, we just need we expected to choose the correct statements. Like, what do we know about partial derivatives? Can we say that partial derivatives do not describe the speed of change of the surface overall, only speed of change by each variable separately? As for me, it sounds like as for me, it's a good question. I think that the correct answer is true. True. Like we don't describe. Formally, for good function, for if a function is differentiable, when in this case we can say that partial derivatives describe the speed of change of the surface overall. Because we have some tricky functions, as you remember, we had an example of function like this one, as you can imagine. So, we had, for example, this function. Am I right? We had this function. Maybe in Q. Like, okay. Like for this function, we know that partial derivatives equal. We know that for this function, I don't remember a proper formula. Modulo of such expression. Yes. We had an example with modulo of such expression. Am I right? Something like this. Okay. But here we can see that with speed of change in or x direction or y direction equals to 0. It's easy to see that it value at point of 0 is 0, and in this direction the speed of change is 0. But we can say that it describes very good the speed of change of surface overall, because you can easily see that in the direction of y equals x, function changes its value much faster when with 0 speed. So that's why we can't say that in any possible situation partial derivative describe the speed of change of the surface overall. Okay?
Sorry, we can or we cannot?
We cannot. We can say it only, it will be true, we can describe the speed of change of the surface overall only for the differentiable function. Only working with differentiable function.
Nikita, sorry, it's also one more question in the chat. If we have some discontinuity in one point in the neighborhood, can we find a derivative? Because in Russian, проколотая окрестность, this is about this or not?
Okay, sorry, I forgot about this question. Like, what do you want to say? Like, we know, I'm not sure where I got the question, because differentiable is much stronger when continuity. So formally you can compute the derivative if your function is if your function has discontinuity at the point of computing. Can you compute the derivative if you have in any neighborhood you have a point of discontinuity? No, you can't do it. You need no, you need continuity to compute the derivative. Like, it's sufficient, it's necessary, it's not sufficient. Okay?
For this topic, I can recommend to watch Khan Academy. I think that the explanation there is awesome.
Yes.
I can send you the links later. I mean, to Sergey.
Yeah, I suggest you to send all the good links you will find in the internet in the chat, because it can be really useful for your colleagues. So I just that's a good idea. So to share convenient materials. I think that education, especially online variant, is based on help one to each other. Okay. did we understand the material about the problem with undifferentiable function? So and why this function is counterexample to the question in this quiz. Okay.
To be honest, the tests are not the trickiest part. Yeah, for example, the second one you already explained. The fourth one is about tangent plane.
How to compute it?
And, yeah, because this one I did. The second one I haven't started yet.
So, what do you want to discuss? So, what do you want to discuss? I'm ready to show you.
Probably for everyone to discuss something more practical, like for example, task number 2, task number 4 in this practical quiz will be probably more useful than the test. So maybe we can try the fourth one.
Okay, it's not a problem. It's just you can suggest me and I will see. Like, okay. Okay, we can compute the tangent plane for this function, but I think it's not an interesting task as for me, because it looks like you can just rewrite it and I don't know how to say подставить. I can't imagine. Oh.
Substitute.
Yes, of course.
Remember.
Thank you. Yes. Sometimes really simple words they leave my mind and I can't use them even in Russian or maybe in English. Okay, so for example, we can easily solve this task, like maybe just in the mind, like because we can say that it's easy to compute the value of this function at the point -1, 1. It's easy to see that this value will be -2, and we know that we have this formula. We know that x is -1. Y is 1, value of a function equals, as we know, equals to -2, as I remember. Yeah, -2, yes. So you'll have something like +2 here. And what do we know about the partial derivatives? It's easy to see that partial derivative over x is y plus 1, so it equals to 2 because y is 1. So we have 2, and here partial derivative over x over y is x, so x is -1, so -1. So the only thing we need is to open the brackets here, yes, like 2x plus 2 minus 1 plus 1 minus z minus 2. So we can easily see 2x minus 1 minus 2x minus y minus z plus 1 equals, so, and we can see that sum of coefficients equals 0. So that's an easy task, as I see. Okay? So I think it's easy to solve. And this task was described. So if you want to discuss some practical questions, we can look for such tasks at the point like here. Looks like what's my tasks, because I added them to the course, because it's an important material how to compute the such derivatives. But okay, so do we want to discuss the tasks from the practice quiz number 2?
I do.
Okay, so let's do it. For example, we have plenty of possibilities to compute such derivatives. The simplest way is just to substitute x and y for sinus t and cosine t, like so, and to compute it with simple derivative over variable t. But we can apply chain rule just to have practice with it, not because it's a convenient way in this situation, but just because because it can be easily done and it can give you a good practice to how to apply this complicated chain rule. So what do you know about the at the point of p over 4? So what do we know about this function? How to compute the partial derivative over t? How to compute the derivative over variable t in for such function? What do we know about it? We know a specific. We know the chain rule. We know that this derivative can be computed like f over x multiplied of x over t plus the same thing for f over y and multiplied on y over t. Okay, I think it's easy to see. We know this chain rule. So applying this rule, we can get the, what do we know about the what do we know about this expression? What will be the f over x? We know that it will be 1 over y plus y over x squared. Okay? I hope it's okay. But it's okay. And we can easily compute the derivative of x over t, like it will be cosine t. And the same story will happen with the second term, but now we'll get minus 1 over square, like and 1 over x, something like this, with minus and with sinus. So for example, we can compute the formula for this expression, for this derivative, using chain rule. And now the only thing we ask you is to compute it at the point of p over 4. So, but you know it's easy to do. You just need to use p. Now you can substitute y and x, for example. You could do it earlier, but for example you can do it right now, and compute the sine and cosine at the point of p over 4. That's not a problem. So I don't want to finish it until the answer. I don't want to find the answer, the number, but I think that's enough. I think much more interesting task is to find, for example, this derivative. Maybe. Okay, it will be. It will have the same specific. Like we can just repeat the actions from the previous task, because you can see that we can apply chain rule. We can just substitute x and y, and we can compute the derivative over t. So I don't know what it's. I am not sure that this task is really useful. So because it's the same like the previous one, I think that it will be enough to save it for your practice. So especially because it's not there is no difference between this one and previous one. Okay. And the first task maybe a bit more complicated, because so I think that it's really necessary to discuss, because usually I see that students have plenty of questions with this task, plenty of problems. Imagine the following thing, that y is a function of x, some anonymous function, and we want to compute its derivative. We want to compute its derivative at the point of 0. We want to compute this thing. So how can we do it? We can apply two important techniques. First of all, we can apply the technique of taking the derivative of this expression. We can find the derivative of this expression over x, for example. What will we get? Left-hand expression will give us the following thing. What will be the derivative of this exponent? What can you say? What will be the derivative?
It will be 0 because it's connected with y.
And no, you are not right, because y is a function of x. Here.
Yeah, of course. It will be a derivative of this function.
It will be
By x.
Yes, multiplied of exponent, or multiplied on derivative of exponent. Like we know that for with computing with derivative, we'll get like fx multiplied on the same exponent. What's nice, what's kind of easy maybe. Now we need to compute this expression, to compute the derivative of this expression. The derivative over x give you 1, so we'll get y. And the derivative over y will give you y over x. So that's the derivative of left-hand equation. Left-hand side, left-hand expression. And what do we know about the derivative of the right-hand equation? Of course, it's 0, because the derivative of constant is 0. So, applying this technique, just simply computing the derivative, we can express our our unknown derivative via x and y, because you can see that we can like do something like with plus x minus y, and we can express our derivative in the terms of y and x. Okay? So that's nice. But as you can see, we still have a problem. We don't know how to compute it at the point of 0, because we don't know the formula for y and for e and y, respectively. So, but what will help? What will help us? We know we have a hint. But we need to use the original equation to find the value of respective y. What does it mean? It means that we want to compute. We don't know y. We know that x is 0, but we can use this technique, use this knowledge, to find the value of y, because we know that this equality holds, but x is 0. What can we say about y?
1.
Of course, that's 1. We can easily see that y equals 1. So that's why we know that if we want to compute this expression, we just need to use minus 1 e in the power of 1 plus 1. And we'll get minus 1 over e over e constant. So what will be the value of your derivative? We can visualize it a little, applying, for example, with one of my favorite resources for plotting of graphs, named Desmos. And you can see that we can build a curve. And we can say that what can I say? That it looks like somewhere it. Oh no. Okay, maybe I'm not right, and it's not easy to see. But it looks like somewhere it crosses the axis, and somewhere we can compute the. Okay, because not 0 but e. So using this formula, we can easily see that one can find the derivative of this function, and it will be it looks like it will be like 1 second, please.
I think it should be minus 1 because e to the power 0 is 1, not e.
Sorry?
I mean the computation, because when we pick x equal to 0, in the denominator we got e to the power of 0 plus 0.
Why?
No, it's y, because it's my mistake.
So, yes, and here you can see that our computation is correct, because you can see that we have a good derivative. You can see that this line is tangent for our curve, for red curve. Our green line is a tangent for red curve. So everything is okay. So I think that this task is kind of usually this task is kind of problematic. So maybe this talk will be useful for you. Okay.
It will.
Hmm?
It will. The lab you explained us in the previous lesson, and it really helped me to understand what do we need to do in the lab.
Oh, it looks like so. I'm glad to hear it because usually students face a lot of troubles with labs. So it's good that you had with you that it helped you to get it what to do. Okay, it looks like we still have some trouble with questions in here. It's a real disaster. Okay, it looks like one of the questions from, but question number 2 and question number 3 in this in lab in this practice quiz are the same one. So it looks like I'll have a look and I'll find the original question number 3 because it's really disgusting that we can't find it. That we lost some material. But okay. Any more questions? It looks like we discussed all the practice, all the interesting practice questions from these quizzes. And for example, I can suggest you some interesting task of extended level of complexity, with extended level of complexity. But I will just show you some interesting things about some beautiful things from the mathematics, like this one. I can suggest you something like this.
Sure, yeah.
For example, there is an interesting question. We know that usually we saw a lot of different continuous functions. We saw a lot of different differentiable functions, and usually we saw that if function is continuous, it usually is continuous in some neighborhood of this point. Like that's a normal thing, but because continuity is like it's like possibility to draw your function without pauses, without breaks, without any shifts and so on. So, but is it possible to find a function that will be continuous only in one point? What do you think? Is it possible? Can we construct such function that it will be continuous only in one point? So it will be such specific point in such interesting function that, for example, here function is continuous, here function is continuous, but in the neighborhood, in all points of its neighborhood, function will be discontinuous. Is it possible? What do you think? That's a complicated question, so I don't expect a mathematical analysis from you. I just expect for your suggestions.
So from the definition of continuity, we have to find limits for this function that resist.
We need the following thing, yes, like this limit equals to value of this function. But so,
yeah,
is it possible that we have this limit in one point, only in one point, but in the neighborhood, this equality doesn't hold? For example, in the neighborhood. So I suggest you to type plus if you believe that such function exists, and minus if such function doesn't exist. So it's just informal game, informal quiz, theoretical practice quiz online. So as I see, only Elvira has an opinion about this task, has some opinion about this task. So, and this opinion is quite right. Yes.
Because I checked in the internet already.
So maybe we can write something like x equal to some value and then another function below, like 2 parts of the function.
Like
or y equal to some value on a point, like y equal to constant, and then some thing that has no limit, for example. So
I'm not sure where I got it.
like for the bracket, and you have y equal to constant for such value of x, and for another values of x, you have another formula. I think it should be like this, like two parts.
Oh, but so, yes, and we but yeah,
Like I proposed. Yeah.
you know, but we still, yes, it's a good idea to use some formula one formula for one for some type of x, for some type of x points, and our formula for other. And Elvira found the how to say, the box of Pandora, opened the box of Pandora, and found a wonderful function named function of Dirichlet function. So it equals to 1 if x is rational, and 0 if x is irrational. So we have some specific function. Can you imagine it? I think that correct answer is no, because it's unreal to imagine such a tricky function. It sometimes it's 1, sometimes it's 0, and in a neighborhood of your of any point, you can see that this function has really close points with highly different value. If your x is rational, when in any neighborhood of your x, you can find an irrational x, and the value of this x will be irrational. So, and you will have like a difference of size 1 between 2 points in really close neighborhood. So this function is everywhere discontinuous, as you can imagine. This part is okay. So this function is always discontinuous. Okay? Well, nice. But I want to make, why do I need it? Because I want to build a function which will be continuous only at one point. So, first of all, I can start with a function where it is discontinuous everywhere. So, how can I build a continuous function at one point from this terrible function? Where is a specific idea that we can, what's the problem of this function? Why is it always discontinuous? We discussed it earlier, but the problem is that values at rational points highly differs from values in irrational points. But we can do the following trick. We can introduce this function, x dx. What do we know about it? It will be x in rational points, and it will be 0 in irrational points, at irrational points. So formally it will look, as you can imagine, it will look something like this one thing. I'm not good at drawing, but you can just imagine that this plot is beautiful. So, what can we say about this function, about this interesting function? Why this function is good from a point of view of my question? Why it's related to my question about continuous only at one point function? Maybe you can see something from the plot. So I really try to do it as such beautiful as it possible. So
Because it will be like 0.0.
yes, you can see that you can use 0.0, but at the point of 0, this function will be continuous only in one point, like x dx, the point of 0, x is 0. What can we say? What can we say about this limit? X dx if x tends to 0, what can we say?
It tends to 0 because 0 multiplied by 0 is 0.
Yes, but we have two different variants. With if we use irrational x, when in this case this multiplication will be 0 because the x is 0. And if our x is rational, when this value equals to x, and if x tends to 0, when x tends to 0. So we know that this function, that this limit equals 0. So that's why this function is continuous at the point, at the 0 point. So, and I think it's a really beautiful example. And what can you say?
Yeah.
And why is it discontinuous in all other points? What can you say about it?
From the definition of limit.
Yes, that's a good and universal answer. Why a function is discontinuous? Because it has a conflict with definition of continuity. Yes, you're quite right. Yes, because we know that taking any other possible point, if this point is rational, when in every neighborhood, like in every in all other possible rational points, you have some value, non-zero value x, and in every neighborhood, you will find a point with value of 0. Yes, we will find a
0
rational
and
point.
0 doesn't belong to, yeah.
Yes, and taking epsilon that equals to modulo of x over 2, you'll find in any possible neighborhood for every possible delta, you will find such point that the difference between values is more than epsilon. So that's a problem. The same story with irrational points. But okay, our main topic was differentiability. And can you imagine, now can we build a function that will be differentiable only at one point? What can we say about differentiability of this function? And what's the definition of differentiability?
So at point 0 it exists because in point 0 it's continuous at least, and we have a constant, and differentiable of a constant is 0.
No, we don't have constant
But
because
it-
you can see
well,
why rational.
Yeah, but in the of course, yes, it's not differentiable because in the close neighborhood, yeah.
Yes, because by some using rational points we have something we can say that derivative is 1 because it's our function works like y equals x, and using irrational points we can say that our derivative is 0. So we have no differentiability for this point. At this point, we know the definition of differentiability. Like it looks like it equals to
Limit.
this limit, yes. And what can we say? X tends to x0. What can we say? Because and you can easily compute that using rational and irrational points we'll get different values. So that's why this function is isn't differentiable. But but we know that function of Dirichlet is really convenient for counterexamples, and x dx helped us to build one interesting example. How to build a differentiable function from function of Dirichlet, differentiable at one point. Any ideas? Okay, we don't have plenty of time, but we have following one example. We can take x in square dx.
Yeah.
Now we can try to, and we can compute the derivative at the point of 0. It will be the following expression. It will be the following expression. We know that this is 0, this is 0, and what can we say? And this expression and this expression can be easily
We have
simplified.
x.
Yes, can be easily simplified to well-known function of x dx. So, and we know that it tends to 0. So that's why we have a real derivative for this function. This function has a derivative at the point of 0. That's okay. That's the only point for this function, the only point of differentiability. But that's a beautiful example. Formally, your function will look like something like this. Right. So it's not very accurate. And you can see that blue and green dots will build something differentiable. You will find a derivative that equals to 0 at the point of 0. So I think that this set of tasks is really beautiful. So it shows us a beauty of continuity and differentiability and of mathematics. So I think that it's time to finish our webinar. I hope that it was interesting and it was beautiful and maybe even relatable to the course and to your interests.
Yeah,
So,
well, thanks. Interesting.
So that's nice. So see you next week and goodbye.